Okay, so what I want to talk about today is I want to talk about what is stress and what the difference is between normal and shear stress and what exactly is going on with that. And so to do that, the first thing I want to look at is I want you to imagine here that we have a sort of a rod with a length with two different pieces with two different diameters. And so you think back to statics when you look at this, and you'll see that from my drawing here, the first piece has a diameter of about 1 inch, and the second piece has a diameter of about 2 inches. And you have a force pushing down on this full length of about 200 pounds. And so if you look at this, and well, before we go to that, the first thing you do in statics is you draw a free body diagram to solve this problem, right? Because we want to know what type of force is going on from the ground when you're pushing down on this. And that's pretty easy, that's pretty simple. If you were to draw that free body diagram, you'd have this length, and you'd have 200 pounds pushing down, and you'd have a reaction force of 200 pounds pushing up, right? So 200 pounds. Okay, so that makes sense. So if you were to look at this though, and think about what would break first, the top part with the smaller diameter or the bottom part with the bigger diameter. And if you thought about it intuitively, you'd say, well, yeah, the top would break first, right? Because it's got a smaller diameter and it's weaker, right? And the reason that is because of stress. This smaller piece has a greater stress going on inside of it here at point A, for instance, than this piece down here with the bigger diameter. And so what stress is the amount of force over the cross-sectional area. So you'd imagine this 200 pounds distributed over however this cross-sectional area is. And because this has a smaller cross-sectional area, so like if you were to look at this at point A and you cut it, the area of that cross section right there, that area is going to be a lot smaller than this area down here. Okay, so since that area is smaller, it's going to have more stress and it's going to break first if you were to put so much force on it. So the formula to remember here in finding stress is for this, and this is called normal stress. Normal stress is when the force is going straight down perpendicular to the cross-sectional area. And so we'll talk about shear stress later and what the difference is, but right now we're just talking about this. So the formula for normal stress, and the symbol we use is sigma. That's a sigma. The formula is P over A. And P is your force, that'll be your 200 pounds here, and A is your area of the cross section right there. And so I want to find out how much stress is going on at point A here. I want to find out how much stress is going on here at point B. So let's do that real quick. Okay, so we want to know what the sigma is, the stress is at A. And so we're going to say, okay, 200 pounds divided by whatever this area is. And so you know it's a circle. They're both circular cylindrical pieces. So the cross-sectional area will be pi over the radius squared, right? So you have pi here times the radius, which is half the diameter. And you'll have to watch that. It'll often give you the diameter, not the radius, so we have to keep track of that and know what's going on. So it'll be 0.5 inches squared. And so when you calculate that out, that comes out to be about 254.6 psi. And that's pounds per square inch. And so when you do the same thing for the stress at B down here, then you'll find that the stress would be 200 pounds over the cross-sectional area, which is pi times 1 squared, because the radius here is 1. And that'll come out to be about 63.7 psi. And so you can see from that, from doing the calculations, that the stress up here at A is a lot greater than what's going on down here in B. We already knew that intuitively because we know that since the area of the cross section up here, it's a smaller piece, it's probably going to break first, and therefore the stress is going to be a lot greater. And so that's what's going on with normal stress. It's a pretty simple concept to understand, but just make sure you understand and can visualize what's going on in the piece. And so the next thing I want to talk about, since we know that the stress is dependent on the area, it's also dependent on the force. And you'll sometimes come across a situation that looks a little bit different than that. For instance, let's say we have a piece that has the same cross-sectional area all the way down its length, and we'll say it has, and we're going to do it in metric this time, it'll be fun, 8 newtons force, and the diameter of this piece is, we'll say, 10 millimeters. And we know that, but we also have a force, we'll say, being applied right here at the middle. For some reason, not actually sure about it, it's 4 newtons. Something is pushing up at it right there in the middle. And so if you were to do statics on this, probably you know that it must be in equilibrium. You'd do the sum of the y's, and you'd know that this down here is 4 newtons. And so, let's see, A and B. Okay, so we want to know where the greatest amount of stress is in a piece like this. The diameter is the same, so like you might think it's going to be the same type of stress across, but you got to keep in mind what are the forces like all the way through this piece. And so first I'm going to try and see what the internal force is here at A. So I'm going to cut the piece as if I was cutting it at A. I'm going to solve it statically. 4 newtons down here and 4 newtons down here. And then an unknown force, Fy here. And so if you were to solve it statically, you'd know that it's still going to be 8 newtons at A. A is 8 newtons. So that's not too bad. We expected that to happen that way. Next, though, we want to solve like what the force is going to be like at B. So we're going to cut it at B. I'm going to solve for the F of y there, 4 newtons. And when you cut the piece to solve for a spot, you can you just solve it from one side, and you can forget about everything that's happening on the other side. We're looking at it from the bottom to right there. And so we know then that the force, the internal force going on at B has to be in equilibrium there. So it's got to be 4 newtons. And so that's interesting. The internal forces are different in this section as they are in this section. And so we know then that the stress is probably going to be different as well, because we know about, remember the formula? Stress is equal to P over A. So the forces, therefore, are going to be different. So when we solve for this upper piece with the stress over the cross-sectional area, you'll find that the stress is going to be equal to about 101.9 kilopascals. And then the sigma and that's sigma A. And so the stress at B, sigma at B, is going to be equal to 50.9 kilopascals. So the important thing that I want you to understand from doing this is understand what stress is exactly, and then what is affecting stress, and never make the assumption really that the stress is going to be the same across through the entire piece, because it's going to depend on what's going on within the piece. If we want to know what the stress is right there at A, you have to solve for the forces at A, and use the cross-sectional area at A, and you'll get something different than when you do the same thing for B. And so just make sure that you understand what's happening with what you're working with. And yeah, and so that's normal stress. And so the only difference between normal stress and shear stress, you do the same thing with shear stress. The formula for shear stress is more or less the same thing, although they do use different symbols. For shear stress is symbolized with tau, another Greek letter. Greek letters are fun. And then they have V, which is shear force, just like P was for normal force, and then that's over the cross-sectional area. And so what shear force is, compared to normal force, this was normal force, going down directly through the piece, and shear force is going in from the side, parallel to your cross-sectional area face. And so when you're solving for the stress for shear, you'd use whatever this force is, we'll say 200 pounds, and then whatever the area is of that face that it's parallel to. And you do the same thing. And the rules apply more or less the same way as they did for normal stress. And yeah,